in a straight line motion, the net force acting on the body is in the direction of motion. And if this net force acts at an angle to the direction of motion at any instant, the object is moved along a curved path. And motion of objects like a bicycle wheel, an electric fan, a spinning top, a merry-go-round, and the motion of the Earth about its axis are only a few examples of circular and rotational motions. So now, let's proceed to period and frequency. So, period and frequency are physical quantities that are used to describe both circular and rotational motions. And the period is simply the time required for an object to make one complete revolution. The number of revolutions completed by the object in a given time is called the frequency. And using the terms frequency and period, we can describe the motion of a bicycle wheel. So, suppose the rear wheel makes 5 revolutions in 1 minute. Therefore, frequency F equals 5 revolutions per minute or 5 RPM. And this quantity may also be expressed in terms of revolutions per second or RPS. That is 1/12 RPS. If the wheel revolves 5 times in a minute, so each revolution takes 2/10 of a minute. 1 minute over 5 revolution or 0.2 minute per revolution. The period T of the bicycle wheel is thus 0.2 minutes. And hence, you can see that the frequency and the period are closely related. They are simply reciprocals of each other. The relationship is shown in the equations F equals 1/T or T equals 1/F. Period may be expressed in seconds, minutes, hours, or years. Correspondingly, the frequency may be expressed as revolution per seconds, revolution per minute, revolution per hour, revolution per year, and etc. So now, let's proceed to the main topic, which is about the circular motion. And circular motion simply is the motion of a body along a circle. If an object moves in a circular path at a constant speed, its motion is said to be uniform. And uniform circular motion is the simplest kind of circular motion. Okay, consider a ball whirled about on a string, and the ball moves at a constant speed. The speed of the ball may be computed if you know the ball's frequency and the radius r of its circular path. The radius is equal to the length of the string. Okay, recall that the speed is defined as the total distance traveled divided by the elapsed time, which is Vs equals d over t. And we can use this equation to find the speed of the ball. The distance traveled by the ball in one revolution is equal to the circumference of the circle that represents its path, that is c equals 2 pi r. The elapsed time is equivalent to the period t. Okay, by substitution of these quantities into the equation Vs equals dt, the speed of any particle in uniform circular motion, also known as tangential velocity, is expressed as V equals 2 pi r over t.
So, we're going to discuss about the centripetal acceleration and force. For an object in uniform circular motion, the speed is constant. But this does not necessarily mean that the velocity is also constant. The velocity is continuously changing because the direction of motion is also continuously changing. At any point in the curved path, the direction of the velocity is tangent to the circular path. Since the velocity is changing, the object is accelerating. From the Newton's second law, you know that if an object is accelerating, there is a net force acting on it to keep it in motion. In the case of whirling ball, a force acts on the string to keep the ball in uniform motion along the circular path. This force is known as centripetal force, or denoted as F sub c, is directed towards the center of the circular path. To keep the speed of the object constant, the magnitude of this force must also be constant. The centripetal acceleration, which is A sub c, is formulated as A sub c equal to b squared over r. The equation for the centripetal force may be determined by using Newton's second law of motion. The formula is F is equal to m times a, which is F is force, m is mass, and a is accelerations. But in this topic, we're going to change the F and A by adding subscript C, so it will represent as centripetal force and centripetal acceleration during computation. Earlier, we mentioned that centripetal acceleration, or A sub C, is formulated as b squared over r. We're going to use that to substitute for the formula, so it will look like as F sub C is equal to m multiplied to b squared over r. So let's have a problem solving. A little girl is playing with her pujong. The ball in her pujong is in uniform circular motion and makes 20 revolutions in 4 seconds. For letter A, what is its frequency? We know that frequency is how many revolutions or complete cycles is there within 1 second. And it is also formulated as 1 over t. So it is mentioned that it makes 20 revolutions in 4 seconds. So we're going to substitute this given to the formula. So we will get as 20 revolutions divided by 4 seconds, and will end up the answer as 5 revolutions per second. For letter B, what is its period? For the period, it is said as the reciprocal of the frequency, and it is formulated as E is equal to 1 over F. So for the frequency, we already had the given, which is we solved earlier, and it is 5 revolutions per second. So we're going to substitute that, and it will look like as T is equal to 1 over 5 revolutions per second, and then the answer that we will get will be T is equal to 0.2 seconds. For letter C, if the length of the plastic cord that holds the ball is 0.8 meter, what is its speed? So for the speed, the formula is V is equal to 2 pi r divided by T. So we're going to substitute the given of the period, which is 0.2 seconds, and the value of radius, which is 0.8 meter. And it will look like as V is equal to 2 pi multiplied to 0.8 meter divided by 0.2 seconds. And then we will get the answer as 25.12 meter per second. If for letter D, if the ball has a mass of 3 grams, how much force is acting on the ball to keep it in uniform circular motion? We're going to use the formula of centripetal force, which is F sub c is equal to m b squared over r. So, but before that, we're going to convert first the mass, which is 3 grams, into a kilogram by multiplying the 3 grams into 1 kilogram divided by 1000 grams, so that we can cancel the units, and then we will get the answer as 0.003 kilogram. We need to convert this so that we were able to change the unit of the force into Newton. So for the centripetal force, we will have as 0.003 kilogram multiplied to square of 25.12 meter per second divided by 0.8 meter, so that we will have the answer of F sub c equal to 2.37 kilogram meter per second square, or 2.37 Newton.
Another example of an object moving in a circular path is a fast-moving car, rounding a curve on a flat, round surface. If the car makes a left turn, the passengers are thrown outward due to the centrifugal force, which disappears when the car stops or returns to a straight path line. Outside the car, the road exerts an inward pull, centripetal force on the car. This force is supplied by the friction force of the tires and the road. Therefore, centripetal force is equals to friction equals to coefficient of friction times the normal force. This equation shows that the maximum possible value of the frictional force is proportional to the normal force pushing the surface together. This normal force is related to the mass and weight of the car. That is, normal force equals to weight or mass times gravity. Substituting, centripetal force is equals to coefficient times mass and the gravity of the earth. Putting everything together, coefficient of friction is equals to v squared or velocity squared over rg or radius times gravity of the earth. This is the condition that must exist to keep the car traveling around the curve without speeding. If the required force is larger than the friction force, the car begins to speed. Now, let's move on to the banking of curves. Why are some curved roadways tilted from the horizontal? We have discussed that a car making a sharp turn is kept in a curvilinear motion by friction. Friction supplies the needed centrifugal force. If the surface of the roadway is smooth, the centrifugal force due to friction might not be enough to keep the car rounding off the curve. Because of this, some curved roadways are tilted. In this case, the centrifugal force is supplied not only by the friction but also by the roadway. The force exerted by a horizontal roadway on a car is equal to the weight of the car and acts upward. In a tilted roadway, the force exerted by the roadway acts in two ways: upward to support the weight of the car and horizontally to supply the needed centrifugal force. Now, let's quiz them. A 1,200 kg race car makes a turn of radius 50 meters at 70 km per hour. If the road is banked at an angle of 16 degrees, will a friction force be required? If so, how much is this force? Now we know that tangent theta is equals to centrifugal force over weight. Centrifugal force supplied by the bank road. Centrifugal force is equals to weight times tangent theta, or centrifugal force equals to mass times gravity times tangent theta. Centrifugal force is equals to 1,200 kg times 9.81 meter per second squared tangent to 16 degrees. Now, the centrifugal force supplied by the bank road is 3,372 Newton. Centrifugal force is equals to mass times velocity squared all over radius. Centrifugal force needed to make the complete turn. Centrifugal force is equals to 1,200 kg times the velocity of 70 km per hour times 1,000 meters over 1 km times 1 hour all over 3,600 seconds squared all over 50 meter of radius. The centrifugal force needed to make the complete turn is equals to 9,069.93 Newton. Now, the friction force is equals to 9,069.93 Newton minus 3,372 Newton. Friction force needed to complete required centrifugal force. Friction is equals to 5,697.93 Newton friction force needed to complete required centrifugal force.
Rotational motion. How would you describe the motion of the child in the merry-go-round in the park? The child undergoes circular motion, while the motion of the merry-go-round is considered as rotational. Now, what is rotational motion? Rotational motion is the motion of the body turning about an axis. The spinning top is one example of this motion. The Earth's motion is both rotational and circular. It rotates about its axis once every 24 hours, while revolving around the sun once every year. What quantity should we use to describe how far an object has rotated or how fast it is rotating? Consider the merry-go-round above and observe point A. It rotates counterclockwise. We can see that A changed position. The merry-go-round has rotated through the angle as labeled. This angle represents the angular displacement. Now, what is angular displacement? Angular displacement is usually expressed in degrees, revolution, or radians. If you use a protractor, you will observe that one complete revolution is equal to 360 degrees. The angle may be measured in terms of radians by dividing the arc of length, which represented by S, by the radius, which is R. If point A earlier makes one complete revolution, S is equal to the circumference of the merry-go-round. Next one, angular velocity. Similarly, we can get the angular velocity by dividing the linear motion velocity, which represents V, by the radius. angular velocity may also be referred to as rotational velocity or rate of rotation. It is a vector quantity and you can specify the direction as positive, counterclockwise, or negative clockwise. The next one is angular acceleration. A rotating object may be described not only in terms of how far and how fast, but also how it changes its angular velocity, how speeding up, slowing down, or changing direction. The time rate of the change in angular velocity is called angular acceleration. The defining equation is angular acceleration is equal to change in angular velocity all over the time. Also, we can compute for the angular acceleration by dividing the linear motion acceleration, which is a, by the radius.
Finally, here are the equations for linear and rotational motions at constant acceleration. For linear, we have final velocity is equals to initial velocity plus acceleration times time. Next is S or displacement is equals to initial velocity times time plus 1/2 times acceleration times time squared. Next is final velocity minus initial velocity equals 2 times acceleration times displacement. For rotational, we have final angular velocity is equals to initial angular velocity plus angular acceleration times time. Next is angular displacement is equals to initial angular velocity times time plus 1/2 times angular acceleration times time squared. Next is final angular velocity minus initial angular velocity is equals to 2 times angular acceleration times angular displacement. After that, let's have a short quiz. So, let's have this problem. A record turntable spins smoothly from rest with an acceleration of 0.52 rad seconds squared. How long does it take to reach 33 revolutions per 3 minutes? Determine the number of revolutions the turntable makes. So with the given values, let's use the third equation, which is final angular velocity is equals to initial angular velocity plus angular acceleration times time in order for us to find or solve time. So let's substitute the values that we have in this equation, and since the problem doesn't state what is our initial angular velocity, we're going to assume that our initial angular velocity is 0. And by doing so, we're going to be left with final angular velocity is equals to angular acceleration times time. And in order for us to solve for time, we're going to divide both sides with angular acceleration to isolate time. Then after that, we'll get time is equals to final angular velocity over angular acceleration. And then let's substitute the values and convert it to rad per second in order for us to cancel the other units and also cancel the square of the time. After substituting the values and converting, we got the value for time, which is 6.71 seconds in order to reach the specified final angular velocity. But we're not done yet, for the problem also asks us to determine the number of revolutions the turntable makes. In order for us to determine the number of revolutions the turntable makes, we're going to use the second equation, which is angular displacement is equals to initial angular velocity times time plus 1/2 times angular acceleration times time squared. So without further ado, let's substitute the values. So again, we have 0 initial angular velocity. So if we multiply it with time, it will just equate to 0. So we will be left with angular displacement is equals to 1/2 times angular acceleration times time squared. So let's substitute the values and convert it to revolution, for it asks us how many revolutions does turntable takes. So 1/2 times 0.52 rad seconds squared times 6.71 seconds raised to 2 times 1/10 over 2 pi rad is equal to 1.8647 revolution. Therefore, answers all the questions from our problem, and that ends our presentation.